Welcome to Albert Center for Theoretical Physics. In this video, I am going to discuss particle quantum gravity, and this is the unsolved problem in fundamental physics. What is quantum gravity? It is trying to understand gravitational force in the framework of quantum mechanics. We know that there are only four fundamental forces in the universe: weak nuclear force, strong nuclear force, gravitational force, and electromagnetic force. Out of these four forces, two has been unified, which is called weak nuclear force and electromagnetic force, and it has become electro weak force. So we are left with electro weak force, gravitational force, and strong nuclear force. And out of these four forces, these three forces can be explained in the framework of quantum mechanics. It means weak nuclear force, strong nuclear force, and electromagnetic force. But gravity cannot be explained in terms of quantum mechanics. We need another theory which is called general theory of relativity, developed by Albert Einstein in 1916. So in the sense that gravitation can be explained only by the classical physics. General relativity is still a classical physics. It is still a classical physics compared to the quantum physics, in which quantum mechanics, quantum field theory, quantum chromodynamics, quantum electrodynamics, all these quantum theories has been developed in the framework of quantum mechanical principle. Now, this whole physics is all about unification. Galileo Galilei and Newton laid the foundation of classical mechanics. Newton especially formulated three laws of motion, and through this we can solve many everyday problem. Also, classical after the development of classical mechanics, Newton also discovered gravity, Newton's gravitational law. Also, when in the early 20th century, there was many natural phenomena which couldn't be explained by the classical mechanical framework. So we needed new what you call mechanics, which is called quantum mechanics. So Planck, Heisenberg, and Niels Bohr, Albert Einstein, and many other developed this framework called quantum mechanics, principle of quantum mechanics, and this helped to explain many unexplained phenomena. Again, electromagnetism also developed side by side from the early ancient time to early 17th century, 18th century. J.C. Maxwell unified this electricity and magnetism into one framework through his four equation. And again, principle of electromagnetism was in direct conflict with Galilean relativity, which laid the foundation of special theory of relativity. Again, special theory of relativity, many scientists try to combine principle of special theory of relativity and quantum mechanics, which gave birth to the quantum field theory. Again, Einstein generalized this special theory of relativity to accommodate gravitational effect, which through which in which it became successful and developed this general theory of relativity. And now we have general theory of relativity to explain gravity, and this theory has well tested theory, and it has predicted many phenomena, and all its prediction has been come true. And we have another field theory, quantum field theory. Now these two are miles apart, and nobody knows how to combine these two quantum field theory and gravitational general theory of relativity. So why we need quantum theory of gravity? Although general theory of relativity can explain almost all the large scale structure in the universe like galaxy formation, gravitational lensing and many others, but when we come near to the black hole, or when we are dealing some natural or some occurrence in near the black hole, then what happened? Uh, then we need quantum gravity, because near the black hole quantum effect becomes much more prominent. So we need quantum theory of gravity to study the gravitational effect near the black hole. And remember, inside the black hole, gravity is infinite, and also there is a large scale, very large space-time fluctuation. So quantum mechanical effect becomes very much prominent, which only we will only understand through the quantum theory of gravity. But combining this general relativity with quantum mechanics is the most difficult problem, and difficulty lies on the 2 points. Point number one, that space time, when Einstein combined in space and time, it became 4-dimension space time. And in general relativity, space time is the dynamic variable. It means we can change it, we can fold it, and we can turn it apart. And but in the quantum mechanics, it is the static. It means it is the fixed background. Like in classical mechanics, space and time is the fixed background. In quantum mechanics too, but in general relativity, it is the dynamical variable. And Minkowski space-time is the fixed background in relativistic quantum field theory too. So this is the one of the major issue, how in general relativity, where space-time is the dynamic variable, but in quantum mechanics it is the background, how we can find the middle ground. This is the one of the burning question in quantum theory of gravitational research. Second is time. Again, time is the given parameter in the quantum mechanics. It is an operator, and in the general relativity it is a dynamical variable. It means time in quantum mechanical framework is different than the general relativity framework. So how to reconcile this problem of time? How we can redefine the concept of time, which will be agreeable both in quantum mechanical framework and both in general theory of relativistic framework. So these two are the burning question in quantum theory of gravitational research. If we able to solve these 2 points, then only we will able to find quantum theory of gravity. And remember, near the Planck length, which is minus 10 to the power minus 35 meter, space-time fluctuation becomes much prominent. So where general theory of relativity breaks down, that's why we need quantum mechanical laws of gravity. So this is the frontier of physics research, where so much activity are going on, and without these two, what you call, these two paradoxes, where in one space time is a dynamical variable, another one is a fixed background, and in one time is a given parameter or time is identical to the time concept of time in Newtonian classical mechanics, but in one time is a dynamical variable. And also we can see that time is dynamical variable in a microscopic world. It means we can see that time changes frequently, but we cannot say same thing in the quantum world. So this is the paradox of two different concept of time in two different theory. So these two are the main issue in the quantum theory of gravitation. If we solve these two main point, then we will find a quantum theory of gravitation. So this is the some little introduction of the why we need quantum theory of gravitation.